It's a great pleasure to be here at DACHFest. This is a great event, and we kicked off with an amazing keynote, and I couldn't be happier to be here in this event, and where we talk about making a difference. And maybe a little bit related to the theme, today what I'm going to talk about is contributing to making a difference in a underrepresented part of the society. I hope this is going to be a fun talk. I will try my best to make it as enjoyable as possible. There are a lot of new tech involved and making a difference. Let's start with the boring bits. This is the usual introduction slide. I'm Arman Amcalar. That's the correct pronunciation of my name. I come from Berlin, here in Germany. I work for a company called UNU GmbH. And I serve as the head of software engineering there. What we do is we build electric scooters, electric motorcycles, much like Vespa, but with batteries. And then we are also inventing tools for the future of mobility and urban mobility. I'm also a founder of something called Lonja Works, which is a software craftsmanship school for women that is completely voluntary, because we have a huge gap to close for the between different genders, and we try to help the best we can. I'm also active on GitHub. I have a lot of open source libraries, from front-end libraries to back-end libraries to brain signal processing and making music with the browser. Most of them are in JavaScript. Almost 90% of them are in JavaScript. It's all open source. Like everything I have written in my personal career is open source. So if you are interested in any of these topics, you can check out my GitHub. Before we start, I'm also a little bit under the weather. I had a flu for the past 2 weeks. So if I cough during the presentation, I apologize for that. I don't want to irritate your ears, but yeah. Sometimes I might need that. So the question is very, very simple. The question is, what is the ultimate hack of our lives? And this came into my imagination while I was attending a meetup in Berlin, and that was called Berlin Hack and Tell. So hackers around Berlin and other cities got together. They do it every month at the end of the month, and they present their hacks. And these are not like software hacks where you hack a web page or something. These are like real-life hacks that you use a device or a technology out of its context, out of its purpose. And I was participating for 2 times in a row with different projects, and I was very fortunate enough to win the title of the best hack of the month 2 times in a row. And then for the 3rd time, I thought if I win it again, they would give me a cup, you know, like the World Cup. If you win it 3 times, you get to keep it. Because there was a trophy that they were giving out, and then you take it back every month. And the question was like, you know, what can I do more to impress these amazing people, these amazing hackers? What is the ultimate hack? And well, I looked no further than myself and my brain. In fact, I had the idea that maybe we can do something with the brain. We can type with the brain. Now, obviously, this idea is not new. It's been around for a very, very long time. And I think last year, or maybe the year before, Elon Musk came up with the idea of a new company, Neuralink. And what they do is they build a high-speed highway between your brain and a computer. So they are building brain-computer interfaces or human-machine interaction devices. And what they aim is to open your skull and put some electrodes there that will transmit wirelessly your thoughts to a computer or your phone so that you can type or communicate with your brain signals. And he had this quote, I think we're about 8 to 10 years away from this being usable by people with no disability. And I'm going to talk a little bit more about that in a few minutes. But, you know, Elon Musk is a great guy, but he's a little bit optimistic about everything, his deliverables as well. And this is not gonna work in 8 to 10 years. In fact, this field is being tackled for the past 30 years now. It started in 1988, and we still have like 20, 30, or maybe 50 years to make this work with real people, with people with no disability. There's a distinction between people with disabilities and able-bodied people. Obviously, it's a lot straightforward. We treat able-bodied people like mice, lab mice, because they respond perfectly to whatever you give to them. So we do the research on them. But in fact, the actual target is disabled people. So if you have ALS, if you have locked-in syndrome, and if you cannot move your arm or eyes or any muscle, in fact, you still deserve to communicate with the outer world, because you can think. There is nothing wrong with your brain, your mind, other than that your body is paralyzed. So it has its own difficulties and challenges working with people with disabilities in this context, but the end goal is to make this a part of everybody's lives, especially people with disabilities, so that they can, they are back in the game. So Facebook also made an announcement right after that, I think 1 or 2 months after that, after Elon Musk, and they said, we're also working on brain-computer interfaces. And they said, our goal is to build a brain-computer interface that lets you type to your mobile phone. You don't dictate with your voice, you just think, and you're going to be able to type much faster than you can physically type with your fingers. So this is like a superhuman ability, or this is going to be. And she was a little bit realistic. She said, this is going to be there in 20 years. So we're just kicking off, and it's some future technology, so bear with us. We'll take some time to make this a reality. Now, this is a picture from, I guess, 8 years ago, from 2010. This is me in the picture, if you couldn't identify by now. And this is my assistant. No, I'm kidding. She was my best friend. She is still my best friend. And she was helping me out with this experiment. This is right before a live broadcast where I demonstrated a brain-computer interface where I typed with my brain signals in real time on TV. And I was getting ready for that. And this was 8 years ago. So this tweet is from January 6, 2010. And I typed it with my brain signals, with all the smileys and everything. And I tweeted with my brain signals. So no motor neurons involved or no muscles involved in the making of this tweet. And it's still there, I think, in my profile. So if you go way back, 8 years back, you can see that this technology is actually reality right now. And I'm here today to talk about how we do this with JavaScript, because that is the hack part of it, right? It's great to be able to type something from your brain, but it's even cooler if you can do it with only JavaScript and nothing else. Obviously, this was part of my master's thesis back at the university, and I was using MATLAB, C++, C, and C# all together to make this happen, writing low-level drivers for EEG headsets and the UI in C#. That wasn't a good experience. And all the classification algorithms, we call them machine learning algorithms right now, but that's a fancy name. So all the classification algorithms were in MATLAB, and it worked really good. You can type up to 20 to 25 characters per minute. So it's like every 2-3 seconds you can type a single letter. And if you think this thing works with locked-in patients, it's the world of a difference for them. One day you have no ability to communicate with your loved ones, and the other day you can type like one letter or one symbol, like an emoji as well, in a few seconds. That's a huge, huge difference. And that's why I picked up this topic again. So a little bit introduction on EEG. Raise your hands if you know what EEG is. A lot of people, that's great. Raise your hands if you ever saw an EEG recording like this. Okay, great. EEG means electroencephalography. So the basic idea is we have electrodes on your scalp, and they track the electrical activity in your brain or on your skull, not in your brain, obviously. This is a non-invasive operation so that we don't delve into our brain, but we gather whatever we can from your scalp. Hence, that's why I'm bald, because it works best. You know, life sometimes has this push, a little help, like when you want to do research about brain signals, life takes away your hair from you, and it's a perfect match. So this is one of the earliest EEG recordings in history that's done by a German scientist called Hans Berger. I'm not making the name up. I know that's the most common German name, Hans and Berger, but it's a real name of a very well-known scientist in Germany in 1924. So he had the idea that the brain is very powerful, so maybe we can record electricity out of it. And he came up with this experiment, and this is one of the earliest recordings of brain signals. However, the scientific community mocked him. They shut him out, and nobody believed him. For about 10 years, he was struggling with this. He lost all of his credibility in the scientific community. But after 10 years, some people were able to replicate his results and his experiments that, you know, some people have different electrical activity in their brain. And then they restored his career. But this is what happens to very early people. If you're an innovator like this, you face the risk of being mocked. But he persisted on, and the story is a happy ending story. And he was, he's the founder of this whole EEG thing. And now, we treat millions of patients every year with this technology. So it's a groundbreaking thing. But one thing you'll notice here is that obviously the resolution of the data is not that interesting. It's almost like a sine wave. Both on the bottom and on the top as well. And obviously the equipment of the past was unable to gather high frequency, high quality data from the brain. It was still useful though. This was still useful. And nowadays we have huge improvements in technology, and also we digitalized obviously everything. And what this means is we now get very quality signal out of the brain. And right now, it almost looks like noise. If you ever saw audio noise, it almost looks like noise because it includes your brain signals plus all the electrical and magnetic noise around you. Therefore, the best experiments are done in something called a Faraday cage. Raise your hands if you know what a Faraday cage is. Yeah, so it's completely isolated magnetically, so even God can't see you inside. And there are no interceptions from any mobile signal, wireless signal, radio signal, whatever, and you and your brain signals only. And that is the safest place to run these experiments. But yeah, so it's very, very high quality, like 96 kilohertz sampling rate, which is really high for brain signals, which are from 0 or 1 hertz to maybe 30 hertz. So we have a lot of signals that we have that we can work with, and the challenge is actually huge. But hopefully, I will be able to demonstrate how this thing works in JavaScript. So I built a node application, an Electron application for this, and let's see if it's going to work. It might not. Yeah. Does not. Because that's how live demos go, right? Most of the time, it just doesn't work. So this is me sitting in my home with the same headset, with the same laptop, and I'm demonstrating how the typing actually works. Do you wonder how it works? Is this interesting to you? Yeah. Thank you. So there's a countdown, and basically, what I do is I just stare at the screen, and the computer knows what I want to type. Here, I'm trying to type a message, hello. That's the first word in hello world. So that's also on my Twitter profile. If you go to my Twitter profile, it's the pinned tweet, so you can watch this afterwards. So I just stare at the screen. There are letters there. These, if you cannot... Uh-oh. That was the wrong button. Let's skip forward. Yeah. If you cannot identify them, these are letters of the alphabet, and they are flashing. They are randomly flashing. And I want to type one single letter. I think I now want to type E, and I'm looking at E. Okay? And whenever E flashes, I'm counting it internally. Oh, sorry, this is still the H. And let's do the exercise. So I'm looking at E right now, and whenever it flashes, I'm going to count. 1, 2, 3, and so on and so forth. And after a certain amount of data being gathered, the system knows that you are being excited about a single letter, and that's E. And all the other letters, when they're flashing, they don't mean a thing to you. So obviously, I mentioned the quality of this headset, and that it's a consumer-grade headset. That's why it takes a significant amount of time to come up with the letter. But you can run any machine learning algorithm or any classifier, TensorFlow, or whatever you want in order to identify these patterns of these brain signals. So it's actually very simple and kind of a boring watch. So I just look at the screen and I cannot move. I'm not allowed to move because, again, this headset uses contact lens solution. Have you ever tasted it? The contact lens cleaning solution? Raise your hands if you ever tasted it. Yeah, 1, 2, perfect. Yeah, yes, I love you. Of course I did, because it looks like water, right? There has to be something special in it. What is it? It has some salt in it. It's a salty solution, saline solution we call it. And that's the perfect thing for this headset because it increases the transmission of electrons from your scalp to the electrodes. So you just wet the pads here, the electrodes, put it on your hair or your bald head, and then you get nice signals. Obviously, in real life, in the hospitals or in actual research, we use gels that are very sticky and that are really hard to get out of your hair. Hence, I had to use myself as a research subject when I was doing this research. But sorry. But the idea is that if you move your head, obviously there is no strong connection between the electrodes and your head. And these signals are on the order of microvolts, like 10 microvolts, 20 microvolts. That's very, very small. And when you move your head, the muscles come into play. And obviously, oh yeah. Yes, I was able to type hello. And yeah, I then right away posted this on Twitter, of course, because why not? But if you move your head, what you see is, in fact, there is a lot of noise, both due to your own movement and the movement of the electrodes. It's actually a very yeah. I mean, you can imagine the level of excitement that I had, right? It was huge. So how do I move forward? Yeah. All right, so how does this black magic work? What is the underlying mechanism for this thing? Now, we have 100 billion neurons in our brains. 100 billion neurons. It's like the number of galaxies in the universe. It's a lot. It's a huge number. And currently, I have 14 electrodes on my scalp. And the best devices that are external, that are non-invasive, have like 256 electrodes, which leaves you with 400,000 neurons per electrode. Okay? which means we actually don't know what's going on in your brain. We have no idea. What we get is a single electrical lead that gives you the sum of 400,000 different neurons firing in different directions. And the worst part is, these electrical signals are vectors. We're at a university, so I can maybe talk a little bit about math. These are vectors that have an amplitude and a direction. So one neuron is firing this way, okay? The other neuron is firing this way. When you sum them up, what do you get? 0, right? So imagine how many neurons fire in all the ways of 400,000 neurons. And what you end up with is, mostly 0. You don't really get a lot of signals. Obviously, in certain situations, you get certain signals, but it's really, really hard to get quality signals from the brain. But obviously, if we had a way to go inside your brain and to implant electrodes there, we could even read your dreams. In fact, there is research being done for this. Even with external high-resolution electrodes, we can read what people see. So it's like a live feed of what you see. Because all you see actually is information that's been transferred to your brain and is processed on the back of your skull. And by just reading there, we can see what you see. Obviously, very, very low resolution, but research is being done on this. Okay, so there are some chemical reactions of potassium and sodium that exchange, one neuron exchanges potassium and the other one gives sodium. And then there is a potential difference, which basically means voltage. There's a voltage difference, and this is what we measure from the brain. Now, if you open the skull, you can, with the consent of the person, of their family, of their hospital, and of the government, because the patient has to be terminally ill, because the probability of losing the patient is really high if you open their skull, and implant electrodes. Some people receive it very well. Some of the brains just reject the electrodes, and terrible things can happen. That's why this is not going to happen in the next 8 to 10 years. Maybe it's going to take 50 years to get all the governments on board and to make this technology a safe technology to operate. But if you can do that, then you can implant thousands of electrodes inside the brain. Then you have a lot more visibility in the actual firings of not individual neurons, obviously, because nobody can use 100 billion electrodes, but at least a little bit more resolution. But the underlying idea is, unfortunately, we just don't know how it works. And that is the worst bit about this. Okay, so what I just showed you on the video is something called a P300 signal, and it's called the oddball paradigm. Why the oddball paradigm? Because I have 35 different letters that I'm not interested in. I'm only interested in one symbol or one letter, and that is odd. The probability of that flashing is very tiny with respect to the other ones, and therefore the name is the oddball paradigm. And this has been first published about in 1988, 30 years ago, by Immanuel Donchin. They were able to write or type 2.3 letters per minute, and then we were able to expand this to further 10 letters, 20 letters, and further. So I already talked about how this thing works. It works based on randomly flashing letters in a matrix, and what you see is that there is an action potential 300 milliseconds after you see the letter flashing, and you're excited by it. If you look at the graph in the black one, you see the actual signal that we're interested in, and if you can read it after 0.3 seconds, 300 milliseconds of the original signal, you see a peak in the signal, in the black signal. That is what gives us this notion of, yes, this is what the person is looking at, so this is what they actually want to type. You gather hundreds of these and refine your judgment about what letter they want to type. The thing is, the red one is the other signal, all right, the regular signals. So if you can separate the black from the red, you can do this task. It doesn't look like really hard because there is a certain difference in between these signals, but obviously these are refined. These are averages of, again, about 50 to 100 different signals from both for the black and the red groups. Usually what you see is the difference is not so clear. Sometimes you just focus on a different letter because your attention just diverges. And you get a lot of false positives, false negatives, and it's the machine learning task to make sure you can separate these black from red. So how do you start with JavaScript? Any JavaScript developers here? Please raise your hands. Okay. It's okay to admit if you're a JavaScript developer. I'm a proud JavaScript developer, and I'm here to prove to the world that JavaScript can do anything. Desktop mobile applications and brain signal applications, although it didn't work previously because of the headset. Raise your hands if you know JavaScript. You don't have to, yeah. All right, so everybody can read this code, right? It's actually very straightforward in plain language. Constant mind requires widths. Then you do mind open, and open your mind. And then you read your mind to the console. Now, let's see if this thing is, sorry, is going to work, because it looks like I have connection. Yeah. So these are the real-time brain signals. Thank you. Obviously, you cannot discern what the individual signals mean, and you get a lot of muscle movements when I'm talking, when I'm speaking, or when I'm moving, even when I'm moving my hands. So it's pretty much all the information is invisible to the eye, but there is only two types of information that you can see with your eyes, and that is, for example, when I'm blinking. And now, let me do it. So you see the peaks, right? 1, 2, 3. The peaks there are the cause of the blinks. My eye blinks. And in fact, they're not even brain signals, they are your muscle signals, because I have a lot of electrodes around my eye here. Now, there are a huge ton of misinformation or disinformation about this online. People claim that it's easy to read brain signals, and they do all sorts of things with their brain signals, but what they usually do is they use the muscles and muscle signals, because they are at least an order of magnitude bigger or higher than actual brain signals. So again, when I blink my eye, that is what you see, and that's mostly through my muscles. And I can play with my jaw. And again, I'm moving a lot of muscles on my face, and these are all muscle movements. These don't contain much brain signals or information in your brain signals. Okay, I'm glad that this demo worked. Let's maybe move on to the other one. So I'm going to type const mind require widths, right? Mind.open, and mind.read console.log. Now, hopefully, when I run this, what you will see is, yeah, here it is. Basically, a JSON log of your brain. So, thank you. So what you have is the battery percentage, the counter numbers, so you can track each frame, contact quality in an arbitrary fashion, the gyro, so you can also track your head movement, and the levels of each electrode that's present in the system. Obviously, these are just numbers. So if you know how to work with numbers, you can do anything with your brain signals. And yeah, this is an infinite loop of brain signals. And every 7 milliseconds, it's like 128 hertz. Every 7 milliseconds, you get one signal or one reading from your brain, and it's up to you to aggregate them and make them work. I wrote a C driver for the headset, but then everything else is in JavaScript. So Node.js bindings, and then basically all all the operation is in JavaScript. There's another. By the way, this tool is open source. So if you want to check the source code, fork or contribute to it, you're welcome. There's another one called Brain Monitor. That is like a command line monitor, just like this. I mean, the same thing in your command line. Let's see if it's going to work. So you just type Brain Monitor. And yeah, it does. And you see the peaks there. This is running in your command line. You can run this in whatever machine you like, in the cloud as well, if you like. So, but yeah, you can upload your brain to the cloud, right? All those buzzwords that don't mean anything. But you can see the gyro on the top right corner, and when I move my head, hopefully you will see the action replicated there. So if you want to do, mouse tracking with your head or something, and your brain signals, clicks with the eye blinks, you can do those type of demos. In fact, the quality is kind of not bad right now. All right, let's go back to the presentation. And the last one is the brain bits. This is the application that lets you type with your brain signals that I demoed in the video. It's also open source. Everything, again, is in JavaScript. It's called a P300 speller because it makes use of these P300 waves or signals in your brain. And it still needs a lot of help, especially with the machine learning algorithm. So if you are into machine learning, please lend a hand. I plan to port it to TensorFlow.js and make use of it. So maybe if somebody wants to contribute, I'm open for contributions. OK, the tech stack is JavaScript all the way up. This thing didn't have native drivers, so I had to write some native C add-ons for the headset to make it talk to JavaScript. But then Node.js is doing the processing. All the machine learning algorithm is running on Node.js in real time, in fact. We use the Electron as a wrapper for the desktop application because you can ship this as a desktop application. And of course, obviously, you can also put it as a web page and have something like a WebSockets or something. I use Vue.js on the front end. Anybody uses Vue.js? Only a few people. Yeah. It's really easy. It's a very, very purpose-built, fast front-end framework. And all the lines that are being drawn are done with Vue.js. I use brain.js. That was an existing library for neural networks. And basically, you can swap in any algorithm that you want. You can use neural networks. Or I use my own classifier from 10 years ago that I wrote in MATLAB. It's a custom Bayesian linear discriminant analysis, something like that. It's called Bayesian linear discriminant analysis. And it's the classifier that I showed in the demo. That is, again, optimized for this brain task. And I had to port it from MATLAB, right? Anybody knows MATLAB? Raise your hands. Perfect. One single character, like the star character for matrix multiplication in MATLAB is like 1,000 lines in JavaScript. I had to write a lot of JavaScript transforming all those functions of matrix transposition and eigenvectors and everything, and had to write or find alternatives in JavaScript, but I did. It worked. And unfortunately, I couldn't find a very good function to give me the eigenvalue of a piece of data. And I still use MATLAB for it. I built a web server in MATLAB to serve the eigen function. So eigen function. So all the processing, all the data crunching is in JavaScript, and there are no web servers. And MATLAB has the web server. So it's the roles are switched between JavaScript and Node.js and MATLAB. And it's serving one single function. If you don't have MATLAB on your computers, that's fine. You don't have to. It's a very expensive purchase. Then you can use the JavaScript fallback, which is not that performant. All right, so what do? We get the raw electrode data that looks like noise. And if you remember the graph that I showed you earlier, it's a section of 1 second after the flash. So after we flash each letter, we take 1 single second, we call it an epoch, and we try to look for a peak right after 300 milliseconds. But obviously, the brain has a lot of information of a lot of different frequencies, so we have to filter them out, especially the low and the high frequencies. So we get a specific bandwidth of frequencies that we are looking for. We then cut the outliers out by a process called Wien serialization. So the top 5% and the low 5% are kicked out. By the way, I'm telling you the secret of my research, which is publicly published anyway, but nobody wants to read 150 pages of math, right? But if you implement this algorithm, you can already start typing with your brain signals. And then we normalize data, because obviously the amplitude of each electrode is different. From time to time it changes, and you have to identify what the peak is, right? Maybe you see a peak, but the actual amplitude is very small. Maybe it's just noise. So you have to make sure you're actually looking at the brain signal and not a radio cell tower or something. So we normalize data, and then we do something called decimation. We don't need that many samples to decide, actually. Does anybody know the Nyquist theorem? Nyquist theorem? A few people. All right, tell me, please, if we are interested in the signals between 1 and 12 hertz, how many samples do we need to be able to faithfully reproduce this signal of 12 hertz max? 24, yes, because it's like a sine wave. You need an end point and a start point to actually, or a midpoint to actually be able to figure out a sine wave. So at the minimum, you need 24 samples if you are interested in 12 hertz. I know this is a little bit technical, but please don't let me lose you. Yeah, so you remove most of the samples because nobody can crunch that metadata, not even MATLAB. And then you apply machine learning. You use either neural networks or custom algorithms, whatever you wish, to identify the red and the black signals, right? All right, so the conclusion is people say JavaScript is powerful when it comes to reading JSON APIs, when it comes to consuming JSON APIs. And what I claim is, yes, it is powerful enough to read and parse JSON APIs, but it's also powerful to read and parse your brain's API. So this is a demonstration of that work. And I kind of open sourced the path into our brains, and now I'm looking for contributors to make brain bits or JavaScript shine again. Please raise your hands if I were able to change your minds about JavaScript. Okay, a few people. That's good. I call it a win. This is a good day. Cool. Yeah, because I claim JavaScript can do anything. I also do music with it. But that's the topic of another talk. So thank you for coming today. And if we have any time, I think we can have some questions. Yeah, a few little minutes. And I might have another demo later in the day at the UNU booth. If you come, you can see me using my brain signals to use the Force in Star Wars. It's very dangerous, so I didn't want to do it here. But I'm going to try to use the Force with my brain signals later. So if you have any questions, maybe 1 or 2 questions, I can have them. Anybody? No? Oh, there's one.
What's the state of hardware in this area? Can anybody just buy this kind of hardware and start hacking around in their homes?
Cool.
Yes.
Yeah, the question is, can you actually buy a hardware like this? Like, can anybody buy it? Do you need ID verification to buy this hardware? No, you don't need IDs for guns, in the US at least, so you don't need IDs to buy this. It's publicly available. This is a consumer-grade hardware. It's about, I don't know, like $700, $800. And if you can shell out that money, you can do brain research at home. Obviously, there are more professional level hardware that you still can buy as individuals, but they would cost you around $20,000. So not that easy. Only the labs can afford it. But yeah, if as an individual you're interested in it, there are a lot of cheaper models as well. But the one that I'm using is kind of the closest to a research-grade hardware that lets you do all of these stuff. The others are just toys. So yeah, this is publicly available, and you can get on board. Any other questions? There's another one over there, please.
You use Node.js to write a JavaScript on the back end. What do you think is the performance like in the browser itself? Do you think it's okay to run it in the browser itself, or do you need
I think it's okay. And if I didn't spend the time, but if you spend the time to move the matrix multiplications into the GPU, it's going to be even faster, especially in the browser. So Node.js uses the same core as the Chrome browser, so it is as performant as the browser, or the browser is as performant as Node.js. So you can already do live transcription of your brain, as we saw it, in the browser as well, and it's going to work. Okay? One more there, please.
You mentioned the practical application in healthcare for someone who's shut in. I'm curious if you're thinking about any other applications, perhaps criminals. Might this be a better polygraph?
Those are very dark waters. But yes, anything is possible. And unfortunately, to be completely honest, I also fear that this tech will go into wrong hands. And if surveillance governments forces you to use this tech against the citizens, it's going to be a nightmare. So it's actually, it can be used as a weapon as well, at least to parse your memories and whatever you see. So that's, think about somebody embedding an electrode in your brain, and then they get live feed of whatever you see, and you cannot turn it off. And it takes your body's power to function, so you cannot also plug the power. It's very, very dystopic, but sorry for bringing down the mood. But yeah, there are a lot of applications. Most of them are very dangerous. Any other questions? One more. Okay, this is the last one. Please. Pushing data to the brain. Yes, it's theoretically possible. Not at this level, obviously, but people claim to do in interesting things. But it's also very, very dangerous for health. You can instantly kill somebody, and that's not a good way. But yeah, it's theoretically possible. So thank you, everybody, for coming today and for listening to me. I hope you have a great conference. Thanks.